So, hello students, I welcome you all on this YouTube channel. So, in the earlier lecture, I have already discussed the process of commutation in DC machines. So, there I have discussed that the reversal of current in the armature coil by means of brushes and commutator bars is called as commutation, right? So commutation is basically short circuit of armature coils by brush, right? Good commutation means no sparking at the brushes and the commutator surface, and poor commutation means sparking at the brushes and the commutator surface, right? So basically commutation process involves the change from a generated alternating current in armature conductor to a direct current, right? So these induced currents flow in one direction when armature conductors are under the north pole, and in opposite direction when they are under south pole, right? So this reversal of current takes place at magnetically neutral axis. So I have already discussed these things in detail in the process of commutation, right? So today I will discuss further the armature reaction, right? So what is armature reaction? Armature reaction is basically the effect of armature MMF on the main field flux, right? What is armature reaction? Armature reaction is the effect of armature MMF on the main field flux, right? So now this armature reaction has some undesirable effects. Yes, it has some undesirable effects. Number one, there is net reduction of main field flux per pole. Due to that, the generated EMF in case of generator falls. So the terminal voltage collapses, it decreases, right? So this is the first undesirable effect, that your net main field flux per pole, it reduces due to the effect of armature reaction, and due to this the generated EMF and hence the terminal voltage reduces, which is undesirable, right? Because in generator what you want? You basically want that the voltage at the terminal, it should not collapse ideally, right? But due to this armature reaction, it collapses, right? If you will not take any adequate measures to avoid this armature reaction, then definitely the terminal voltage in case of generator, it will reduce. Why it will reduce? Because the generated EMF will reduce. Why the generated EMF will reduce? Because the net main field flux per pole reduce, right? So this is the first undesirable effect of armature reaction. We will discuss it further. Second undesirable effect is sparking at the commutator, right? Sparking at the commutator. third undesirable effect is there is distortion of the main field flux wave along the air gap periphery, right? Distortion of the main field flux wave along the air gap periphery. So now first we will see the DC machine at no load, and then after we will analyze it at loaded condition, right? So just have a look at it. This is, I have taken this DC generator at no load condition. That means when no any load is applied, in that case this will be the magnetic field lines from north to south, right, due to main field flux. So when no any load is applied, then definitely there will be no currents in armature conductors, right? So this is unloaded condition, right? So in this case only one flux will exist in the machine, right? There is only one flux in the there will be only one flux in the machine, right? That is field flux due to main field poles, right? So here as you are watching, these straight lines, these straight vertical lines from north to south, they are basically representing the main field flux of the machine, right, in the no load condition, when there is no any load is applied, right? So in this case the position of this magnetically neutral axis will be horizontal, exactly horizontal like this, right? For simplicity, let us consider this is a two-pole DC machine, right? For explanation we will understand, we will consider that the DC machine is of two poles, north and south, right? So this circle which you see inside, this represents the rotor, and this small circle drawn with the red color, these are basically armature conductors or rotor conductors, right? So now this position of this brush is like this on the MNA. I told you, I have explained that brushes are always placed on MNA, magnetically neutral axis, right? So brush axis is MNA. So this green color that you are seeing, this is the position of this brush, right? Now so in this case when you analyze, there is only at no load condition there is only one flux, that is a resultant flux, and this is nothing but the main field flux phi f, right? So phi r represents the resultant flux, and this resultant flux is equal to main field flux, right? So now let us come to other condition when we have applied the load, right? So when you apply the load, as soon as you apply the load, definitely current will flow in armature conductors, right? So first have a look at it on this diagram. So in the loaded condition, when the load is applied, in that case this will be the condition, right? So when the load is applied, in that case the current will flow in armature conductors, right? Armature current will flow. Now can you tell me the direction of induced EMF or induced current in these rotor conductors? For generator, we have assumed that the direction of rotation was clockwise, right? We have assumed that direction of rotation of this generator, it was clockwise, right? So here analyze this and just tell me what is the direction of induced EMF or induced current in these rotor conductors. So for that I told you that you should apply Fleming, you have to apply Fleming right hand rule, So when you apply Fleming right hand rule, then how will you apply? Just take your right hand. So Fleming right hand rule says that if the first finger represents the direction of field lines from north to south, and the second finger represents, and if the first finger represents the direction of field lines from north to south, and if the thumb represents the direction of motion, right, then my second finger will tell the direction of induced EMF on the rotor conductors. So if you analyze this particular rotor conductor and apply Fleming right hand rule, then you will have to do like this, right? First of all, adjust these two fingers and one thumb in mutually perpendicular direction like this, and bring your first finger in the direction of field line from north to south like this, and bring your thumb in the direction of motion, right? So I have already explained that motion of this conductor is tangentially clockwise like this, right? So thumb, it will be like this, and first finger is like this. Then my second finger is coming like this. That means it is away from the reader, and away from the reader is cross. So polarity of this rotor conductor is, polarity of induced EMF for this rotor conductor is cross. So likewise for all the rotor conductors which are under the influence of this north pole, it will be south. It will be cross, right? It will be cross. It will be cross, right? Like this you can apply Fleming right hand rule. So it will be cross, right? Now if you apply the same Fleming's right hand rule to determine the polarity of these lower rotor conductors which are under the influence of south, then you will get dot, right? Just opposite, right? So can you apply? It's very easy. So your thumb is like this in the direction of motion. So if you analyze this particular rotor conductor, then its motion is tangentially like this, right? Clockwise like this, right? This is the direction of thumb, and field lines are from north to south. Then how to apply? Like this, thumb is in direction of motion, right? And first finger from north to south, right? Then my second finger is coming, towards the reader, right? See this second finger, it is coming towards the reader. So that towards the reader means it is dot. It is dot, right? So even without applying Fleming right hand rule, you can directly write the polarity of this lower rotor conductor to be dot, because effect of north will be just opposite to south, right? So if the north pole, under the north pole, if the rotor conductor is having cross induced EMF, then the rotor conductor under the influence of south, it will be having dot, right? So now you have established the polarity of armature conductor, polarity of induced EMF or induced current in the armature conductors, right? So as soon as the armature current will flow in the armature conductor, because you have applied the load, so armature current will flow in the armature conductor. So due to this they will be having their own field, right? Armature conductor will be having their own field, which was not there earlier in the no load condition, but now it is there due to the loaded condition, right? So when the load is applied, the current will flow in armature conductor. They will be having their own flux, that is armature flux, right? So now when you apply Fleming's right hand rule, then you get cross in these rotor conductors, and you will get dot in these lower rotor conductors, right? So now when you apply right hand palm rule, this is my right hand, apply right hand palm rule. So these forefinger, they will be in the direction of this induced currents, right? So due to this cross, you will have to apply fingers, you will have to apply fingers like this. That means it must go away from the reader, right? You cannot do like this, that if you do 4 fingers like this, that means it is coming towards you, right? But for the upper rotor conductors, the current is going away from the reader. That is the meaning of cross, right? I have already explained. So now when you apply Fleming's right hand rule like this, then due to this cross, these fingers, it will be going away from the reader, showing the cross polarity of induced current, and they will be coming due to the south route. So here if you apply Fleming right hand rule, then you are getting this cross in south. So if you apply right hand palm rule to determine the direction of armature flux, it will be towards this direction, which is shown by this arrow, right? So this is phi AR, representing flux due to this armature conductors, right? So this phi AR is like this, and this field flux, it was from north to south, from top to bottom, right? So now you have 2 fluxes in the machine. Due to this loaded condition, you will be having armature flux, right, also along with this field flux. So now due to this armature flux and this field flux, the resultant flux, it will not be just perpendicularly downwards, right? So it will be having some intermediate position like this, right, like this. So this is the position of resultant flux in the loaded condition. Just take a parallelogram law and you will come to the fact that your resultant flux due to this armature flux and field flux will be somewhere in between these two, like this, right? So this is my position of resultant flux phi r. Now as soon as the resultant flux is established in the machine, right, it will be responsible for the crowding of the main field lines, right? So resultant flux phi r is responsible for crowding of main field lines at trailing pole tips of generator, right? So see how crowding of these field lines takes place. These upper rotor conductors, I have drawn it separately, and the lower rotor conductors, I have drawn them separately. So these cross, they will be having the magnetic flux which is clockwise, right? Why clockwise? You can apply right hand screw rule, right? So right hand screw rule, when you apply on this cross rotor conductors, that means when you rotate this clockwise, right, then the field that will be established, that will be inside, right? That means the current, the induced current which are going away from the reader, it can only be obtained by due to this cross, due to this clockwise magnetic field, right? So it is just like when you see any pen, when you rotate it clockwise, then it is going downwards, right? And when you rotate it anti-clockwise, then it is going upward. Or when you look at it, So when you rotate it clockwise, right, when you rotate it clockwise, then it is going away from the reader, right, that is cross. And when you rotate it anti-clockwise, then it is coming towards the reader. So that's the process of understanding that's how you can understand. So this, due to this cross, the field will be clockwise, right, and due to this dot, the field will be anti-clockwise. So if you take the combined effect of all these four coils, all these four conductors, this will be clockwise like this, right, it has been shown by this arrow. And when you take this dots, four dots, then the effect of resultant effect, it will be anti-clockwise, right. So now this, due to this cross, the resultant is coming clockwise. So this field lines, they will be pushed toward the right end of this north pole, which is basically trailing pole tip, right. And when you see the condition of field lines due to these dots, right, it will be pushing the field lines towards the left end of the south pole, which is a trailing pole tip, right. So just have a look at it, how to determine the trailing pole tips or leading pole tips. For that, you will sit on this rotor, right, and this rotor is rotating in clockwise direction, right. So now first of all, you will be hitting this edge, right. So this will be the leading pole tip because you are hitting it first, right, and then after you will hit this particular corner, this particular edge of this field pole, that means this is the trailing pole tips. Similarly, when you come here after rotation, when you come here, first you will hit this edge, that means this is the leading pole tip, and then after you will hit this pole tip, that means this is a trailing pole tip. So for north, this is the trailing pole tip, right, for the generator rotation, and here for south pole, this will be the trailing pole tip for the generator rotation. So what I said, due to the effect of this armature flux, your field lines, they will be pushed towards this trailing pole tips of this field pole. So trailing pole tips for north is basically the right end of the pole, extreme right, right, and due to these dots, the field lines, the main field lines, they will be pushed towards this trailing pole tip of south pole, right, that means which is the leftmost point of this south pole, right. So that is shown in this diagram. So just have a look at it. Here in this diagram, these field lines, they are pushed towards the trailing pole tips of this north, and here they will be crowded or pushed towards this trailing pole tip of the south pole, right. So that means due to this crowding of these field lines at the trailing pole tips of these field poles, the resultant MNA, it will be shifted, right, at load, right. So this will be the position of new magnetic neutral axis, right. When load was not there, then the position of magnetically neutral axis was this, right. But as soon as you applied the load, the armature flux will be established due to the current flowing in the armature conductors, right. So this results into the crowding of these field lines at the trailing pole tips in the direction of rotation of generator, that means here and here, right. And due to this, the MNA, the magnetically neutral axis, it will shift from its original position. So this will be the new magnetic neutral axis at load. In the loaded condition, this will be the new magnetic neutral axis, right? So that means now the armature flux, it will be like this. As soon as the MNA will shift, the armature flux, it will be like this in the direction of magnetic neutral axis, right? So this shows the new position of magnetic neutral axis along which you will have armature flux. Field flux is from north to south, that is downwards, like this, vertically downwards, right? So just analyze this. Due to this phi AR that you are watching here, you can resolve this phi AR into two components. One component will be vertically upward like this, and one component will be in the horizontal direction like this, right? So this particular component in the vertical direction, let me call this phi AR demagnetizing. So in the bracket I have written demagnetizing. Why demagnetizing? Let us further discuss. And this horizontal component, let me call this phi AR cross magnetizing, right? Phi AR cross magnetizing. So just have a look at it. This vertical component of this armature reaction flux, that is phi AR, it is called demagnetizing flux. Why demagnetizing? Because it is directly opposing this main field flux phi F, right? See this, phi F is vertically downward like this, and the armature reaction flux is vertically upward, just 180-degree phase difference, right? So this is basically demagnetizing this field flux, right? That means, what is the meaning of demagnetization? Meaning of demagnetization is that it is directly opposing this field flux. Which component? The demagnetizing component of armature reaction, it is directly opposing this field flux, and this component is basically responsible for reduction of this main field flux per pole, that is phi F, right? So what I said, this phi AR, it is directly opposing this field flux, thereby this field flux, the net main field flux, it will reduce, right? Another component is basically cross magnetizing, right? Why it is called cross magnetizing? Because it is directly crossing this axis, right? So that's why it is cross magnetizing. So the component of armature reaction flux which is responsible for reduction of main field flux is phi AR demagnetizing. Only this component will be responsible for reduction of this main field flux. Why? Because it is directly opposing this field flux, right? So due to this, the net main field flux, it will reduce. As soon as the net main field flux will reduce, the generated EMF Eg is equal to K phi omega m. That means that generated EMF will also reduce. See here, right? So if the generated EMF will reduce, then definitely the terminal voltage of the generator will also be reduced, right? See here, Vt is equal to Eg minus Ia Ra. So if the generated EMF will reduce, then terminal voltage will also reduce. That means terminal voltage will collapse, right? So why the terminal voltage collapses? Why the terminal voltage reduces? It is because the reduction of generated EMF. Why the generated EMF reduces? Because the net main field flux reduces. Why the net main field flux reduces? Because of this demagnetizing component of armature reaction flux, right? So this all phenomena is taking place due to the fact that due to shift of this magnetically neutral axis. Why magnetic neutral axis shifts? Because of the effect of this armature reaction, right, on the net main field flux, right? So what is armature reaction? Armature reaction is basically the effect of armature MMF on this main field flux, right? So due to the effect of armature flux on the main field flux, this all phenomena is happening, right? So this is armature reaction. So armature reaction has three undesirable phenomena, like I have already explained. Number one, there is net reduction of main field flux per pole. Due to that, the generated EMF in case of generator falls or reduces, so the terminal voltage collapses, or you can say decreases, which is undesirable, definitely, right? Second is sparking at the commutator. Now see here, if for the MNA shift, if the MNA shifted due to the load, if you allow the brushes to remain at their original position, then definitely sparking will occur, right? And why this sparking will occur? Because the coil will be having some induced EMF, and during the time of commutation, when they will cross this MNA, then during the time of short circuit they will give sparking. So that's why you must shift these brushes along the direction of new MNA. If you will not shift these brushes, then definitely the sparking will take place, right? I have already explained this in the process of commutation. So if these brushes will be allowed to remain at their original position, then the coil which were placed at this MNA at no load condition, then during the time of commutation, when they will cross this MNA at no load axis, then during the time of commutation, during the time of short circuit, they will give sparking. So to avoid this condition, the remedy is to shift these brushes. If you will shift these brushes at the new MNA, the new magnetically neutral axis, then definitely this sparking can be reduced, it can be minimized. So brush shift will be the remedy, but definitely for large machine, shifting the brushes every time for the change in load is not manually possible, right? So for that we will use compensating winding and the interpoles in the interpolar region to minimize the effect of armature reaction, right? That we will discuss in the next lecture, right? So today in this lecture, what I have discussed that what is the effect of armature reaction, what is armature reaction, and what are the effect of armature reaction, right? So I will be concluding this topic, right? So what is armature reaction? Armature reaction is basically effect of armature MMF on the main field flux, right? आर्मेचर का फ्लक्स मेन फील्ड फ्लक्स के साथ जो छेड़छाड़ करता है, दैट छेड़छाड़ इज नोन एज armature reaction, right? So this armature reaction has this undesirable effect. There is net reduction of main field flux per pole. Due to that, the generated EMF in case of generator falls. Second is sparking in commutator, and third is distortion of the main field flux wave, right, along the air gap periphery. So this is due to this armature reaction, the net main field flux wave, it got distorted, right? It will be distorted. So that is a third undesirable effect of armature reaction, right? So when you load the machine, then current will flow in this armature conductor. Armature flux now will be developed. It will be resulting into the crowding of these field lines towards the trailing pole tips of the generators, right? So due to this, the magnetic neutral axis will shift, and if you will not place your brushes along this new MNA, new magnetic neutral axis position, then definitely you will get a sparking, and also the collected EMF or the generated EMF will reduce, right? So these are the undesirable effect. So this is the armature reaction. So I will stop. Thank you very much. Thanks for watching.